Good evening, everyone. I'm Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to this week's live interaction for the NPTEL course in Engineering Mathematics 2. This course has the code NOC 23MA25. In this week, we'll be looking at the concepts covered in week 11 of the course. These include integral transforms, specifically Laplace transform, its properties, what is a function of exponential order, when is when would Laplace transform exist, different properties such as first and second shifting, change of scales, derivatives and integrals, as well as looking at Laplace transform for periodic functions. With that in mind, as is the custom for every week, we'll be looking at a few selected problems which will help us further elucidate the concepts taught in this week's lectures. Problem number one. This asks the Laplace transform of the function f of t is equal to t square plus at plus c, where a and c are constants. Okay, so we can see that the function f of t is essentially a polynomial in t, and what we'll do is this is a polynomial function. So what we'll do is we'll look at the general function p of t, which is given by summation an t raised to n, where n goes from 0 to infinity. So, or n goes from 0 to say capital N. So this is my capital Nth order polynomial, and we are interested in finding Laplace transform for this particular polynomial. We can see that we essentially have a0 is equal to c, a1 is equal to a, and a2 is equal to 1, and a3 onwards, a3, a4 onwards, all vanish to 0. So this is our Laplace transform, this is our polynomial p sub capital N looks for this particular function f of t. Now, if I were to look at Laplace transform of say a and t raised to n, it's nothing but a n times Laplace transform of t raised to n. So this is because the Laplace transform is, as you know, it is linear. So were I to only consider the Laplace transform of t raised to n with the condition that n is greater or equal to 0, this is essentially, or greater, n is greater than 0, this is essentially integral of 0 to infinity e raised to minus st t raised to n dt. So the Laplace transform of t raised to n, where n is greater than 0, is nothing but, we'll now do integration by parts. So we'll integrate the term e raised to minus st and differentiate the term t raised to n. So we essentially get t raised to n into integration of e raised to minus st. So it's e raised to minus st upon minus s with the limits 0 and infinity, minus integration from the limit 0 to infinity. Now we'll take the derivative of t raised to n, which is n times t raised to n minus 1 e raised to minus st upon minus s dt. Suppose s is a, suppose we also have the condition that s is a number greater than 0, then e raised to minus st would essentially vanish. Then e raised to minus st with the limit t tending to infinity is essentially 0. And similarly, t raised to n at limit t tends to 0 is also 0. So the product of t raised to n into e raised to minus st, provided s is greater than 0, will vanish out both at t equal to 0 and at t equal to infinity. So my Laplace transform of t raised to n ends up looking like minus So we take this n outside and we take this minus s outside. Minus n by minus s, integral 0 to infinity t raised to n minus 1 e raised to minus st dt, which you can observe is nothing but n by s times Laplace transform of t raised to n minus 1. Notice that we had taken n to be greater than n to be greater than 0. So the minimum value of n is 1, which means that t raised to n minus 1 is nothing but e raised to 0, which has the minimum value, n minus 1 has the minimum value of 0, which should make the Laplace transform of 1. And if we remember our basics, Laplace transform of 1 is nothing but integral 0 to infinity e raised to minus st dt, which is e raised to minus st by minus s with the limit 0 to infinity. Again, we take s greater than 0 for this term to be convergent, because when s is negative, e raised to minus s will become positive and t is plus infinity. So this whole thing will blow up and not converge. So we again have this restriction s being positive, which gives us 0 minus 1 upon minus s. So this is 1 by s, which gives us Laplace transform of t to be equal to, which is t raised to 1. So n becomes 1. So 1 by s Laplace transform of t raised to 0, which is nothing but 1. So t raised to 0 equals 1. So Laplace transform of 1, as we know, is 1 by s. So Laplace transform of t becomes 1 by s square. Similarly, Laplace transform of t square becomes 2 by s times Laplace transform of t, which is nothing but 2 by s cube. So totally, our Laplace transform for the function f of t becomes Laplace transform of t square plus at plus c, which is nothing but Laplace transform of t square plus a times Laplace transform of t plus c times Laplace transform of 1. Laplace transform of t square is 2 by s cube. Laplace transform of t is 1 by s, so a by s square. And Laplace transform of c is 1 by s, so c by s. So this is the final answer that we are looking for Laplace transform of f of t, which if you look is nothing but option B. Okay, so hope this problem is clear. It's a simple problem which goes back to how Laplace transform is calculated for polynomial functions. Okay, if there are no doubts here, we move to the next problem number 2. Problem number 2 is essentially asking us to calculate Laplace transform of the function f of t is equal to cos of t plus 2 sine of t. So we know that the Laplace transform would require cos of t and sine of t. So we'll just quickly derive it for the general form. Cos of kt is nothing but e raised to I kt plus e raised to minus I kt by 2. Similarly, sine of kt is similarly sine of kt is e raised to I kt minus e raised to minus I kt by 2i. Again, if we were to take Laplace transform of cos of kt, it would be nothing but half of integral 0 to infinity e raised to minus st e raised to I kt plus e raised to minus I kt dt, which is nothing but half of integral 0 to infinity e raised to minus s minus ik into t plus e raised to minus s plus ik. into t whole into dt, which if you were to simplify is e raised to minus s minus I k t upon minus s minus I k going from 0 to infinity plus e raised to minus of s plus I k upon minus of s plus I k going from 0 to infinity. Now you can notice that this, if s is negative, minus s becomes positive, and as t goes to infinity, this whole thing would blow up. So we require the condition for convergence that s is greater than 0. In which case, if you think about the term at t going to infinity, this e raised to minus st would vanish, whereas e raised to minus e raised to plus ikt would essentially be something of the form cos theta plus I sin theta. So 0 into cos theta plus I sin theta, which should again be 0. So 0 minus, when t is 0, the numerator becomes 1. So 1 upon minus s minus ik plus 0 minus, same thing, 1 upon minus of s plus ik. So were I to take these two terms together, they are 1 upon s minus ik plus 1 upon s plus ik, and I would multiply the first term numerator and denominators with s plus ik, and for the second term multiply the numerator and denominators with s minus ik. So my whole thing would become half of s plus ik plus s minus ik upon s square plus k square. So this will cancel out, and therefore Laplace of cos of kt would essentially become 2s 2s by 2, so which is s upon s square plus k square. This is Laplace transform of cos of kt. Similarly, if we are to repeat this procedure again for sine of kt, we will get sine Laplace transform of sine of kt. The only thing that has to change in the derivation is how we input the formula. So you would have 1 upon 2y e raised to ikt minus e raised to minus ikt. And then again we substitute the limits with the condition that s is greater or equal to 0, or s is greater than 0, which should give us convergence, and thus our Laplace transform for sine of kt would end up looking like k upon s square plus k square. These are both important formula when it comes to calculating Laplace transform for general sine and cosine trigonometric functions. And for our case, we have essentially have L of f of t is nothing but L of cos of t, which is cos of 1t plus twice of Laplace transform of sine of 1 into t. So basically k is 1 here for both cos and sine terms, which would give us s upon s square plus 1 square plus twice of 1 into s square plus 1 square, which is nothing but s plus 2 upon s square plus 1. This is Laplace transform of f of t, s plus 2 upon s square plus 1, which is option number 8. Option A, rather. Okay, so in this problem, we looked at Laplace transforms for general sine and cosine function, which the formulas you can later on use conveniently for different sine and cosine functions which may arise. Problem number 3. Now we are asked to calculate Laplace transform of function e raised to minus 3t plus s. Okay, so first thing to notice, if we have a function f of t is equal to, general function would be f of t is equal to e raised to minus 8t plus b, or e raised to 8t plus b. If this is my general function f of t, then my Laplace transform of f would look like integral 0 to infinity e raised to minus st e raised to 8t plus b dt. I could decompose this to essentially be e raised to 8t into e raised to b. Now e raised to b is independent of time t, so it can be brought outside of the integration, and we would get something like e raised to b integral 0 to infinity e raised to minus of s minus a t dt, which would look like e raised to b times e raised to minus of s minus a t upon minus of s minus a from 0 to infinity. This is convergent only if s minus a is a positive number. So the whole thing would look like e raised to b times 0 minus 1 upon minus of s minus a, so which is e raised to b upon s minus a. So Laplace transform of e raised to et plus b would look something like this. So this gives us a general formula. For our case, f of t is equal to e raised to minus 3t plus 6, which means that a equals minus 3 and b equals 6. Therefore, my Laplace transform of f would look like e raised to 6 upon s minus minus 3, which is e raised to 6 upon s plus 3. So this gives us our specific solution for the Laplace transform of this particular function. So which is e raised to 6 upon s plus 3, option D. In this particular problem, we looked at a linear an exponential function which are linear in the argument t, or could be in x, and then calculated the Laplace transform for this general linear exponential. Problem number 4. It asks us to calculate Laplace transform of the function t sine t. Okay, so here we'll have to make use of the multiplication property, which basically states that I'm, I'm naming this as, I'm using the name multiplication here, which states that let f of s be the Laplace transform of f of t. Then we have Laplace transform of t times f of t equaling minus d by ds of f of s. And it's then generalizable to say t raised to n, and this becomes minus 1 raised to n d by ds raised to n of the bracket. Okay, so how do we, so we can like use this property for our particular function, which where f of t equals sine t. But if we wanted to have a quick look at the general proof, it would go something like this. Laplace transform of, or I'll just take the first derivative of f of s, is nothing but the first derivative of real 0 to infinity e raised to minus st f of t dt. Now you can note that this integration is over. Now you can note that this integration is over time t. So the derivative d by ds can be moved inside. So we essentially have integral 0 to infinity d by ds of e raised to minus st f of t dt, and this derivative is nothing but integral 0 to infinity minus t f of t, e raised to minus st f of t dt, which turns out to be, which essentially gives us Laplace transform of t times f of t to be equal to minus d by ds of f of s. For our case, let us, we are given that f of t is equal to t times g of t, with g of t equaling sine t, which is nothing but sine of 1 into t. So my Laplace transform of g of t would essentially be capital G of s, which is 1 upon s square plus 1 square, which is 1 by s square plus 1. And my first derivative of g of s would be minus 1 upon s square plus 1 whole square into into derivative of s square plus 1, which is minus 2s upon s square plus 1 whole square. I'll just box this thing here. Okay, so by this multiplication property, my Laplace transform of t times g of t is nothing but minus d by ds of g of s, which is 2s upon s square plus 1 whole square. So where do we have this? We have this as our option D. Okay, similarly, you can prove this property for the general t raised to n into f of t condition. Laplace transform of t raised to n into f of t becoming equal to minus 1 raised to n, the n derivative with respect to s of f of s. Okay, so this covers an important and pretty useful property in Laplace transforms. Problem number 5. Now we are asked to now calculate the inverse Laplace transform. Okay, so let us see. We'll be trying to decompose this function f of s, capital F of s, into its partial fractions. So we have capital F of s equals 3 upon s square plus 2s, which is nothing but 3 upon, if I factorize the denominator, that is s into s plus 2. Okay, now we want numerator to be a linear combination of the factors of denominator. So I could write a into s plus b into s plus 2 to be equal to 3, which would give me a plus b times s plus 2b is equal to 0 times s plus 3, which essentially gives me a plus b equaling 0 and 2b equaling 3. We will solve the second equation initially. So b equals 3 by 2, which means a equals minus 3 by 2. So my function capital F of s looks like minus 3 by 2 into s plus 3 by 2 into s plus 2 upon s into s plus 2, which if you think about it is nothing but 3 by 2 times 1 by s minus 1 by s plus 2. Okay, where have we seen this forms 1 by s, 1 by s plus 2? So if we go to and look at the very first problem, we can see that the Laplace transform of 1 is 1 by s. And another thing is Laplace transform of e raised to at plus b is of the form of e raised to b upon s minus a. So we know that Laplace transform of 1, we know Laplace transform of 1 equals 1 by s. Laplace transform of e raised to at plus b equals e raised to b upon s minus a. So we can compare the we can compare the second term with e raised to b upon s minus a, which would give us minus a is equal to plus 2 and e raised to b equaling 1, which means b is 0 and a is minus 2. So Laplace transform of e raised to minus 2t is 1 upon s plus 2. Therefore, my inverse Laplace transform of f of s, which is function f of t, would look like 3 by 2 times inverse Laplace transform of 1 by s minus inverse Laplace transform of 1 by s plus 2, which is nothing but 3 by 2 times 1 minus e raised to minus 2t. So that is option A. So this covers and this touches upon the important concept of inverse transform. As we learned in integral transforms at the very beginning, in general, integral transforms are applied on, say, have been constructed so that they can be applied on PDEs to generate a set of simple algebraic equations, which we can solve, and then in the, say, like the S domain for Laplace, and then we invert the same to obtain our solution in the time domain. So that is the inverse transform is like a very important step in the same. Next we look at inverse transform for a different function 1 upon s cube plus s square. Again we have to do partial fractions. So I have f of s is equal to 1 upon s cube plus s square, which is nothing but 1 by s into s plus 1. I'll take the 1 by s outside and I have 1 by s into s plus 1. It's 1 by s into 1 by s into 1 by s plus 1. I can decompose into partial fractions. That would essentially end up being 1 by s minus 1 by s plus 1. You can look at this and see very quickly that this is in fact a valid decomposition. So I have got 1 by s square minus 1 by s into s plus 1. Again this I can again decompose. So I have got 1 by s square minus of 1 by s minus 1 by s plus 1. So my transformation looks like 1 by s square plus 1 by s plus 1 minus 1 by s. So this is how my function capital F of s looks in terms of partial fractions. Again, we can take the inverse transform. So we know that 1 by s is basically Laplace transform of 1. And we know that 1 by s plus 1 now is Laplace transform of e raised to minus t. Again, we can go through the e raised to at plus b process. And the third one, 1 by s square. If you remember from the very first problem, we obtained this to be the Laplace transform of t. We can go back to the first problem and we can see that this is indeed correct. So Laplace transform of t, if you remember, is nothing but 1 by s square. Laplace transform of 1 is 1 by s. Laplace transform of t square is 2 by s cube. Okay. So that should cover up, that should explain why I have directly written 1 by s square to be Laplace transform of t. So my function Laplace transform of f of t, which is f of s, is nothing but Laplace transform of 1 by Laplace transform of t plus e raised to minus t plus 1 minus 1. So my f of t is nothing but t plus e raised to minus t minus 1, which is option A. Okay, again a simple inverse transform example. Another inverse transform question is problem number 7. So again we proceed the same way. We calculate partial fractions. F of s is equal to 2 upon s square minus 25, which is nothing but 2 upon s square minus 5 square, which can be written as s plus 5 into s minus 5. Okay, and again we proceed using the same way. A times s plus 5 plus b times s minus 5 should equal to 2, which gives us a plus b times s plus a minus b times 5 s. This is s, this is 5, should equal to 0 times s plus 2, which means a plus b is 0 and a minus b is 2 by 5, or 5 times a minus b equals 2. If we add these two together, we get 2a is equal to 2 by 5, which means a is equal to 1 by 5, which also means that b equals minus 1 by 5 because a plus b equals 0. Okay, so my function f of s ends up looking like 1/5 of s plus 5 plus minus 1/5 of s minus 5 upon s plus 5 into s minus 5. So this is 1/5 of 1 upon s minus 5 minus of 1 upon s plus 5. Again, we can do the same exercise, Laplace transform of e raised to at plus b being e raised to b upon s minus a, and we see that 1 upon s minus 5 is nothing but Laplace transform of e raised to phi t, and this is nothing but Laplace transform of e raised to minus phi t. So if I take inverse Laplace transform of f of s, that is nothing but 1/5 times e raised to phi t minus e raised to minus phi t. If I multiply and divide by 2, that is 2/5 of e raised to phi t minus e raised to minus phi t upon 2. Now this whole term is nothing but hyperbolic sine term of phi t, which gives me inverse transform to be equal to 2/5 of hyperbolic sine of phi t. So that is option D. Now we move to problem number 8, where we are asked to calculate Laplace inverse transform of f of s. Again, same similar problem. Again, same method. First, you calculate partial fraction. Again, we use the same method. Partial fractions, which is a times s plus b times s plus 3 equaling s minus 2. So a plus b into s plus 3b equaling 1 into s minus 2, which means a plus b equals 1 and 3b equals minus 2, using which we get b equaling minus 2 by 3 and a equaling 5 by 3. Therefore, my function f of s and capital F of s ends up looking like 1/3 of 5s plus minus 2 times s plus 3 upon s times s plus 3. Okay, which is 1/3 of 5 upon s plus 3 minus 2 upon s. Again, we know that 1 upon Laplace transform of e raised to minus 3 would 3t would be 1 upon s plus 3, and Laplace transform of 1 equals 1 by s. Therefore, inverse Laplace transform of f of s is nothing but 1/3 times 5, 1/3 times 5 into e raised to minus 3t plus minus 2 times 1, which is 1/3 times 5 into e raised to minus 3t minus 2, which, okay, if I take a minus 1 outside, it's 2 minus 5 into e raised to minus 3t, which looks like option C. Okay, so another example of Laplace inverse transform. Okay, so now we are asked to calculate Laplace transform of this particular function t minus 2 whole square into e raised to 4t. And how do we do that? I'll just expand f of t to be t square minus 4t plus 4 into e raised to 4t, which is nothing but t square into e raised to 4t plus minus 4t times, or I'll rather write it as t square into 4t. This is my first term, minus 4 times t into e raised to 4t plus 4 times e raised to 4t. And now we are asked to calculate Laplace transform of f of t. This is nothing but Laplace transform of t square e raised to 4t minus 4 times Laplace transform of t times e raised to 4t plus 4 times Laplace transform of e raised to 4t. Okay, let's start with the simplest term, that is e raised to 4t. For this, we know that Laplace transform of e raised to at plus b. We have already shown this to be e raised to b upon s minus a. So in this case, b equals 0, so e raised to b becomes 1, and a is 4. So this Laplace transform of e raised to 4t becomes 1 upon s minus 4. Now I'll do one more thing. I'll write g of t to be equaling e raised to 4t, which means capital G of s equals 1 upon s minus 4. Now by the multiplication rule that we have seen earlier, Laplace transform of t times gt is nothing but negative first derivative of g of s, which is negative first derivative of 1 upon s minus 4, which is minus 1 by s minus 4 whole square into derivative of s minus 4, which is 1. So this whole thing becomes 1 upon s minus 4 whole square. Similarly, were we to look at the second derivative of g of t, this is nothing but, we can see this is nothing but minus d by ds of Laplace transform of t of gt. So I am now splitting this t into t times gt, so which we know is nothing but the first derivative of g of s. So this whole business becomes the second derivative with respect to s of capital G of s. We already know that the first derivative of g of s, or is the negative of the first derivative of g of s equals 1 upon s minus 4 square. So the first derivative of g of s is nothing but minus 1 upon s minus 4 whole square, which means that the second derivative of g of s is minus 1 upon. So the first thing is s minus 4 whole cube into minus 2, and the derivative of s minus 4, which is simply 1. So this whole thing becomes twice upon s minus 4 whole cube, which gives me Laplace transform of f of t to be equal to Laplace transform of t square into e raised to 4t, which is 2 upon s minus 4 whole cube minus 4 times Laplace transform of t into e raised to 4t, which is 4 times 1 upon s minus 4 whole square plus 4 times Laplace transform of e raised to 4t, which is 4 times 1 upon s minus 4. This is how my overall equation would look like in the transformed space S. 2 upon s minus 4 whole cube plus 4 minus 4 upon s minus 4 whole square plus 4 upon s minus 4, which looks like option C. And finally, we move to the final problem for this for today, and it's an interesting one. We are asked to calculate Laplace transform of f of h is equal to sin h of t, sin of t. So I'll just simplify this. Sin h of t is nothing but e raised to t minus e raised to minus t by 2 times sin of t. So which is half of e raised to t sin of t minus e raised to minus t sin of t. Now we know that Laplace transform of sin of t is nothing but 1 upon s square plus 1 square, 1 upon s square plus 1. Therefore, Laplace transform of e raised to t sin of t would look like e raised to t sin of t would look like integral 0 to infinity e raised to minus st e raised to t sin of t dt, which is integral 0 to infinity e raised to minus of s minus 1 into t sin of t dt. So wherever we initially had s, it's now being replaced with s minus 1. So initially we had s in Laplace transform, now it's replaced with s minus 1, and we are now taking Laplace transform of t with uh, with s minus 1 in place of s. So this whole thing becomes 1 upon s minus 1 whole square plus 1 square, 1 upon s minus 1 whole square plus 1. Similarly, you can see that Laplace transform of e raised to minus t into sin of t would end up being 1 upon s plus 1 whole square plus 1. Again, you write this whole thing here, e raised to minus t, so that becomes e raised to minus of s plus 1 into t. So instead of s, now we are moving to s plus 1, which gives the whole thing f of s, which is nothing but Laplace transform of f of t to be equal to half of 1 upon s minus 1 whole square plus 1 upon s plus 1 whole square plus 1. Sorry, minus 1 upon s plus 1 whole square plus 1, which is half of s plus 1 whole square plus 1 minus s minus 1 whole square minus 1 upon, I'll just simplify this. So the left term looks like s square minus 2s plus 2, and the right term looks like s square plus 2s plus 2, which is nothing but s square plus 2 minus 2s, and s square plus 2 plus 2s. So we essentially have s square plus 2 minus 2s being multiplied with s square plus 2 plus 2s. S plus 1 minus 1 cancel out. S plus 1 whole square minus s minus 1 whole square. So s square cancels out. 1 cancels out, and 2s minus minus 2s. So we are left with 4s. And dividing by half, we end up with 2s upon s square plus 2 whole square minus 4s square, which is 2s upon s square plus 4s s4 plus 4s square plus 4 minus 4s square. So we overall end up with, just do this thing here. So we overall end up with capital F of s being 2s upon s raised to 4 plus 4. This becomes our final answer. So which is option D. Okay. Hope this particular example is also clear. So this marks the end of the problems that I had. If you have any doubts, you may ask them now. Okay, since there are no more doubts for this particular session, I thank you for attending this or watching this online on YouTube. We'll meet again in on next Friday, which will mark as the last class for this particular course. Thank you.